Okay, so let's get started, please. Thank you. Welcome to today's SAMPI webinar. My name is Julieta Barrueta Robles, and I'm a research officer at the National Research Council Canada, and I'm going to be moderating the webinar for today. So as you know, we're hosting these webinars in a monthly basis on different topics, so please stay tuned as we publish this in SAMPI 365 on our LinkedIn page. And if you have any questions, please do not hesitate to contact anyone from SAMPI or myself. So one quick reminder is that right now the abstract submission for SAMPI 2025 in Indianapolis is open, and the deadline is coming up quickly, September 15th. So please, you can go to the website and see what technical tracks are available. And to let you know, this webinar is being recorded, and you're going to be getting the link of the recording within 2 to 3 weeks. Also, any questions that you may have during the presentation, please write them in the Q&A. And at the end of the talk, I'm going to be reading them out. At the end of this presentation, also, there's going to be a very brief survey. Please, I encourage you to fill it in, as it's very helpful for us to continue to deliver the content that you want and the information that you're interested in. And with that, I'm going to introduce Professor Anush Pursartip, who is our speaker for today. So Anush is Professor of Materials Engineering at the University of British Columbia, where he is the Director of the Composite Research Network.
Everybody, welcome back. I think we're still kind of filtering in from lunch, but we'll go ahead and get started again. Recording's turned back on.
Okay.
I get a thumbs up that you can hear me online?
Yes.
Some indication?
Yes.
Make sure things are working. Emote, unmute.
Sorry, there was some interference there. Sorry. So to continue to introduce, Anush Pursartip is Professor of Materials Engineering at the University of British Columbia, where he's the Director of the Composite Research Network and co-director of the Composite Knowledge Network. He's also part-time Director of Research at Convergent Manufacturing Technologies, and he's also a SAMPI Fellow. So with that, please, Anush, go ahead with your presentation.
Thank you, Julieta. It's a great pleasure to have this opportunity to share some thoughts with you on the science and practice of composites process simulation. So I'd like to start off with some acknowledgements. Work thoughts that I'm going to present here are directly and indirectly related to the work of many generations of UBC and Convergent researchers and colleagues. Far too numerous to mention, but I would like to acknowledge multi-decade collaboration with my dear colleagues, Dr. Reza Vaziri and Dr. Joran Fernlund. Similar fashion, I'd like to acknowledge numerous partner organizations, funding agencies, and collaborators over the last few decades, and again, in particular, the Boeing Company, who have been very supportive of our activities at UBC. In presenting this talk, I think it's really important for me to emphasize that it's not possible to provide a comprehensive review of the field. There's going to be an unavoidable bias to our own work, and of course, very much my opinions about where we are and where we're going. So the way I'd like to go is start off by really emphasizing the tight linkage between design and manufacturing of composites, position process simulation in the context of a digital world, talk about digitalization and practice, that is, after all, why we are doing all of this, do a quick dive into process simulation science, talk about how that science is harnessed with technology, give an example of how we're continuing to push the bounds of what we can do, talk about actually then practicing this capability with examples in materials and process design and in production, and then finally a quick summary and conclusions. So let's remind ourselves as to what is both the strength and perhaps the weakness of composites. Typically, when you design, you have a function in mind, and very simply, you ask yourself, what's the best material in the best shape that allows us to achieve that? And then you have to ask yourself, well, can I actually turn that material into that shape? And that is where process comes in. The top triangle, very design-centric. The bottom triangle, manufacturing-centric. And in the case of composites, of course, the process during the manufacturing steps, which converts the thermoset from a liquid to a solid, the thermoplastic, you melt it, you resolidify it, crystalline or semi-crystalline. That gives you a microstructure, and you end up with the properties that you wish for your design. Key point to make, of course, is that that definition of process there is a little too limited. And as this talk is about processing and manufacturing, let's home in on that for a moment. Let's push function out of the way just a little bit. And let's actually think about what the impact of this integrated processing of material and shape means in terms of manufacturing. If you look at certification requirements, they will talk about materials and processes must be defined and stable. You must demonstrate repeatable parts. What does that mean? What that means is whatever you assumed in design, a volume fraction, a degree of cure, apply thickness, you have to maintain those as you go from your development into production. So function, from a manufacturing perspective, is actually replaced by the concept of quality. And so then what we can ask ourselves is, fair enough, what about defining the production a little bit more? And this is where we need to bring in the fact that you generate the material into that shape on tooling using equipment. And so now you get this more complete definition of manufacturing. And then what we can do is say, well, what are the issues with quality? And the answer is, well, I'd like to maintain quality at a certain rate, at a certain cost, and increasingly with considerations of sustainability. So quality is the one thing we're trying to control in manufacturing, in processing. And it turns out that actually defining what quality is difficult. So we have these outcomes. If they're within spec, 2% porosity, that outcome is not a defect. If it's 3%, it's a defect. So what we can do is we can think about these generic outcomes and when they violate some specification. And we have to think back to the origins of how all of this started. So we're going back to the 1960s, 1970s. And of course, today we have this building block approach where we build up from simple panels all the way up to complex structures. And in doing that, what we're doing is we're defining the quality outcomes typically at the materials and process level of the pyramid, way down here. And then we're pushing them all the way up the pyramid. If we actually try to define things systematically, what we realize is this is the defect taxonomy from Potter et al. We're not going to go through it. But what I'm trying to emphasize is that it's actually very difficult to manage quality outcomes in a structured way. But we need to do this. So really, what we care about is the property outcome. It's very difficult to do that. So very often, we control it as a microstructural outcome through NDI. We look at porosity. We look hopefully at thickness, whatever we can measure easily. Very often, we're actually forced to use a proxy such as the process history. So managing the temperature history is the way we go. We've cured enough, but we haven't degraded either because it didn't get too hot. So process simulation is very much one way that we're trying to manage all this complexity. So let's position process simulation in the context of all the digital keywords that we hear around us nowadays. I don't know how familiar you are with the Gartner hype cycle, but I really quite like it. And in the Gartner hype cycle, what they do is they plot expectations versus time, and they talk about how all technologies go through this cycle. And so if we look at AI simulation for manufacturers, which is a buzzword that is floating out there, they would say that that right now is what they call in the innovation trigger phase, where what you're seeing is increasing excitement, increasing expectation for that technology. There's generative AI in design and engineering. There's industrial data management, digital product passports. Then they say there comes a point where you hit a peak of inflated expectations. They're saying that in 2024, digital engineering's up there. And then everybody becomes disillusioned because the value wasn't there. So you then come rushing down the other side of the mountain into the trough of disillusionment. And they say that's where digital twins are right now, model-based systems engineering, digital twins for products. And then if you think about where you go next, I apologize, something went wrong there. Then you enter the slope of enlightenment and the plateau of productivity. Well, back over here, we have funding agency and academic excitement. Over here, you have sustainable industrial and societal value. I would argue that today, process simulation is over here. Why is that? Well, process simulation has been with us pretty well since the early days of the composites ecosystem, going all the way back to even the 70s, certainly the 80s. So we've gone through these cycles, and I'm going to give you examples of that as I walk my way through this talk. And the key point to make is that process simulation was the first wave of all these manufacturing AI digital approaches. And I'm going to argue, and I'm hoping to convince you, that actually it forms the framework, the digital nerve center for all these technologies that are coming along. So let's think about that a little bit more. There's all the buzzwords on the left. And we're trying to bring some structure to this. One of the sort of more structured approaches that appeared out of Germany in particular some 10 years ago was this idea of Industry 4.0, which says how we've moved from basically water and steam power to this world of dancing robots of today. And this is a very manufacturing, factory equipment-centric view of the world. Parallel to that, coming out of the United States primarily, has been this concept of integrated computational materials engineering, which has a science-based approach to it. It's more design, materials, processing centric. And I firmly believe that these really come together. They start bringing together all that digital alphabet soup that we just saw. And if you distill it down, what we basically have is tools to help us make better decisions in design, in production. We have prior data, we have prior experience, we have scientific process simulation as a structured way of looking at that. We have new data, and I'll talk a little bit more about this in a moment, but we have data science techniques, including ML, AI, uncertainty quantification and propagation. And then as we go into the factory, we have sensing, we have automation. Key point to make as we look at all these digital tools available to us, production volume matters. The value of aerospace products, and I'm choosing that as a market, but we could look at any other market, the value is high, but the volume is small. So we've got to be careful about blindly applying lessons from other sectors. These three markets have roughly the same value. 140 million iPhones a year, 8 million Toyota vehicles, about 1,000 Boeing or Airbus aircraft a year. So if you are a machine learning AI expert, you would say, give me 1 million data points. I'll give you a brilliant ML model. Apple would say, that's 2 days production. Toyota would say, that's a few weeks production. Boeing and Airbus would say, that's 1,000 years of production. So clearly, what we need to do is different from those other sectors. So let's think a little bit about the future of digitalization, because clearly we need to understand what tools we have available if we want to make all of this work to our favor. Up to the early 2000s, digital was the domain of engineers and scientists. We had the biggest computers. We did the most computation. And then something changed. All of a sudden, it was consumer applications that drove the hardware and software revolutions of the last 20, 30 years. Today, AI, particularly generative AI, is the talk of the town. You can't actually escape it at the moment. But how do we look at AI in the context of science and engineering. There's no doubt, machine learning is a brilliant tool for basic tasks such as image recognition. If they can recognize penguins on ice floes, of course we should use machine learning to do image recognition of fiber fluff on an AFP machine. But otherwise, we should acknowledge that machine learning is basically a reduced order modeling approach. We should definitely use it, but we've got to use it in a scientific simulation framework. And if you actually look at the literature, people are going that way. We just don't have enough data to do it any other way. Cheap sensors, cheap data associated with those sensors, transformative. The ability to fuse data and simulation using uncertainty quantification and propagation, transformative. All this new hardware, software, the ability to manage huge amounts of data, those are being advertised with consumer applications. We should absolutely use them. But the point I hope to convince you is that all of that needs to come together in a framework where physics-based simulation provides the digital nerve center. So let's think a little bit about digitalization and practice. Right now, because of course everything we make has to be safe, whether it's aerospace or outside, we have what you could call a prescriptive regulation framework. We have lots of rules which are there to make sure that we have guardrails. And so the way to use simulation and digital technologies right now is as a job aid to make decisions faster and better. But you're still doing the old things. You're doing thermal profiles to prove that a temperature history is within bounds. Everything you're doing is based on the old rules. But the thing to realize is that we really need to look to the future, which is you actually change how we do things based on these new capabilities. And you go to basically performance-driven design, where you exercise the science to drive manufacturing decisions. And this is being done at a high level. So what you're talking about is replace a temperature history requirement with a degree of cured requirement. But then you have to make sure that you don't get other bits and pieces wrong. You need to understand what the consequence of those changes are. And then, of course, that feeds into how you capture data in the factory and how you use it. Noting that right now, we actually don't measure a ton. And when we do, we use it in a cell. We don't know how to use it across the factory. So let's do a quick dive into process simulation science. Again, if we think very simply of a little cartoon factory, you have material coming in, you check it, you store it. Let's say you lay it up, you might form it. You then go through a transformation step where if it's a thermoset, you cure. It's a thermoplastic, you crystallize. You'd NDI, machine, assemble, inspect, and ship it off. The very first model that appeared in the open literature was in 1983 by Luz and Springer. And you can actually look at the history before that. But really, people were starting to do simulation in the mid-70s onwards. So very clearly, a technology that was recognized as important at the very dawn of our field. And Luz and Springer really did a brilliant job of not just doing that sort of deep dive into cure, but they also laid out what I believe is the correct way of doing things, which is they talked about a systematic approach where you're tracking the evolution of the material through the whole system using state variables, variables that fully define the system at any instant. And just as a bit of history, myself and my colleagues, we've continued down this path. We got in our first master's thesis, Marc Doroche, in 1988, was just an implementation of what Luz and Springer's had done. And then we've been at it for pretty well 35 years, trying to expand that concept. And so let's think about that for a moment. In that first paper back in '83, what you had was a very simple model. It had a simple material model for the cure kinetics. It had 1D governing equations. There was no representation of the tooling and equipment. But it was disruptive in what it claimed could be done. If we fast forward to today, That same step is modeled in 3D. What you have is a full representation of the tooling and the equipment. So you're meshing the part, the tool, the boundary conditions. You have sophisticated material models, which are represented in the simulation, and you spend a lot of time ensuring that the boundary conditions for the simulation are correct. So you're taking a piece of the puzzle and going very deep. But at the same time, and I think this is a really important point, we're going wide, we're going across the factory. So you have that cell in the factory modeled very carefully, but our models are now starting to go across the factory. So what you're doing is you're saying that at every instant I have the digital twin, if you will, where I define all its state variables in terms of chemical, physical, mechanical parameters, and I run it through the whole factory, and I can actually, at the end of this, pass these parameters to performance models. So theoretically, and increasingly so, we can pass residual stress, local fiber orientation, ply thickness, and so our failure models can be done on the as manufactured and not as the as designed. So I would argue strongly that the future of process simulation is in these holistic integrated frameworks where the interactions across the whole process chain are captured and they're propagated through. And I'll talk shortly about when you propagate it through, you want to actually quantify and propagate the uncertainty with it. I would say that point solutions don't provide the same value and really shouldn't be done in 2024. So what is the state of the art in process simulation science and technology? This is really difficult to do. What I'm showing here is a little table that was created back in 2021, which will likely appear in the next revision of the Composite Materials Handbook 17 in Rev H. And the reason I'm showing this here is to say that for many, many outcomes, our technical understanding, our process modeling maturity level, our analysis results are pretty good. They're usable. There's areas where we need more work. Again, I'm going to show you an example on wrinkling. I may be a little bit pessimistic here because this was 2021, and there's actually been quite a bit of advancement in the last few years. But in general, the issue becomes that the science is improving leaps and bounds, and it will. If I go back here and I talk about thermal management, we have excellent cure kinetics models. We've realized in recent years that there's complexities if you have long holds, which brings in physical aging. So the science for that is being improved, and eventually it's going to end up in the solutions. It's just a matter of time. So what's left? What's left is getting value out of this. It's integrated into practice, disrupting practice. And then we, of course, get this very, very virtuous cycle of improvement. So let's look at process simulation technology for a moment. The key is to realize that as you go from science to technology, it's all about usability. So I'm going to give you a couple of sort of applied examples from our own experience base. We're now at a point where you have libraries of models, and these libraries of models are designed to plug into solvers, be it a standalone solver like the Raven software that I'll show you in a second, or plug into Abacus or ANSYS, or even open source solvers such as OFVM. And fundamentally, these libraries are just a bunch of equations. And these equations cover different behaviors: cure kinetics, CTE, cure shrinkage, modulus development. And the convergent library, for example, has over 140 models in it right now. Key point to realize, and I'll come back to this in a few minutes, is that it actually doesn't take a lot of effort to write these equations, to put them into any software. The issue becomes, how do you use them? And then how do you calibrate them? So let's think about use, first of all. What you have to do is realize that these models, even with today's technology, can be quite compute intensive. So you got to ask yourself, what am I trying to do? Am I just trying to understand the material? Well, that's a 0D analysis. Am I trying to do a quick thermal analysis? Well, then a 1D analysis is good enough for most geometries. Or am I starting to do something more complex where I need 2D or 3D analysis? And your simulation times are going from seconds to hours to days. If you're going low geometric complexity, you're in the world of the materials and process analyst. If you go up the building block, you're into the world of the product, into the world of the structures. Key point is that you have to have common material models and property libraries so that you understand how you're moving up and down this hierarchy of scale. You also need to understand what is the value of doing the analyses at different levels, because there's always a sweet spot where you start and then you continue it through the rest of the analysis. There should be no disconnect. And this again goes to my pitch that integration is really, really important to get maximum value. Let's look at wrinkling. We talked about that as one of the areas where development is ongoing. And this, of course, is really important to us because we have lots of new processes, be it forming, be it automated fiber placement, where we're dealing with this raw material and we're trying to understand how it will deform. And so the answer is the material has a huge range of competing mechanisms that are trying to accommodate the boundary conditions. And some of those deformation mechanisms are benign. For example, shear to a certain extent is a benign mechanism, whereas any axial compressive load on the fibers is source of concern because it's going to give you buckling, it's going to give you wrinkling. And so this is an area of active development, both in the science and the technology. So if I were to look at sort of typical solutions available commercially off the shelf right now, using shell models, shell and solid models in a sort of FE analysis framework, the sort of earliest offering out there is probably PAM form. Then we have our colleagues in the Netherlands with a great software called Adiform, and Convergent also has its forming capabilities. If you look at these, they all have very, very similar capabilities in terms of what's happening within the solution, and there are materials characterization services to feed the beast. And so both Convergent and Adiform, for example, provide that as a service. On top of that, you have a huge amount of academic activity with varying levels of sophistication, generality, validity, and support. So let me give you an example of the kinds of things that are being done at the leading edge. So here what we're doing is we're looking at a tapered C channel. This is a collaborative project that was done with the National Research Council of Canada. And as you're forming this, in this case, we're looking at an extreme example where it was formed at room temperature. You start to see wrinkling in the inside of the corner. And the way that one then looks at that in terms of prediction at the moment is to look at the strain fields and identify zones where the strain field is conducive to wrinkling. And you can also look at things such as the edge of the end of the flange, and you can see that it actually, you're seeing a lot of shearing between the plies, which is actually very desirable. And again, the models pick it up. If we look at, say, a tapered geometry with a kink in the geometry, we will typically get wrinkles, both the inside and the outside of that. And again, if you look at your fiber axial strains, the models will show that. To actually predict the wrinkle directly with dimensions, that of course is leading edge stuff at the moment and really quite difficult and expensive to do. But that gives you a feel for how everything is improving around us as we speak. And of course, there's people who are trying to do machine learning, reduced order models, surrogate models that actually allow you to do this faster. let's move to the practice of process simulation. And the first thing I want to emphasize is that good inputs are critical, even more than if you're doing a structural analysis. The most basic processing material card for a thermoset is the Cure Kinetics model that predicts how the material evolves from a low molecular weight liquid, and as it cross-links, it becomes a gel. Then as the network structure evolves, it actually vitrifies. So the way we create these material cards is we do lots of tests using a wide range of analytical equipment. And right now, of course, we're focusing on the dynamic scanning calorimetry, say, we're using heat flow to quantify degree of cure. And you choose your favorite material model equation, and you fit the data to it. So that gives you the material card for that material, and off you go to the races to do the simulation. Key point to make, and this is old, this goes back to 2008. Don and Dijkman did a nice job going through the literature, finding every 8552 Cure Kinetics model that existed at the time and just comparing them. And what you see is that sure enough, they all predict that the material cures, but you can see a wide range of predictions, including one which is way off. So pedigree, quality really is important. The good news is that we're starting to see more and more libraries becoming available, and this is absolutely necessary for the ecosystem to develop, to stabilize. So here you can see a couple of tables. The one on the right is an open database. A lot of these materials were, in the early days, supported by funding from the US government. Increasingly, the material suppliers are funding these because they're starting to see big value in providing these to their customers. The table on the left is a more restricted list that is available to contractors for the US government. There's, of course, lots of material model libraries that are held in a proprietary fashion by companies that have adopted process simulation early. So uncertainty in your material inputs is critical. Another one, which I think is really important, is uncertainty in your heat transfer coefficients in thermal process simulation, which is otherwise a very stable technology. And here, what's happening is you get very complex airflow in an oven or an autoclave. If the load is large, or you have a mixed load, and you really need to understand what your HTCs are, because with airflow, the heat transfer coefficient actually plays a big role in thermal lags and actually thermal leads. So a lot of work has gone into trying to measure that. And again, here you could get yourself into a world where the best approaches are uncertainty quantification, Bayesian inference, a sophisticated mixed mode data collection, and data analysis methods. And I'd like to put in a pitch for a talk in the upcoming CAMEX 2024, where my colleague Arganil Bhattacharjee will talk about how this can be done very professionally and very quickly. So let's move on to actually some materials and process design examples. So let's go back to the beginnings. Let's talk about cure cycle optimization, finding a cure cycle that'll give you a decent degree of cure. Remember that hype cycle? One of the leaders in pushing process simulation through has been the Boeing company. And what I'm showing you here is an example of a project which was done in the early 2000s, funded by DARPA, called the AIM-C program. And here what you're seeing is the use of the simulation capabilities 25 years ago, where a 3.5-inch thick laminate was cured without an exotherm. And the analysis was done manually by an expert, by Dr. Carl Nelson, who was at Boeing and is now unfortunately retired. And he came up manually with an optimized cycle, about 700 minutes worth. And it took him about 8 hours using the tools of the time. And here you can see the response when that panel was made, and you can see that he did a brilliant job of predicting it and giving us a valid panel. So this was done around the early 2000s, and since then, we've used this as a case study, and you can now do that same analysis using very quick software, using theory-guided machine learning as a surrogate model to explore the space quickly. And basically, you can do this analysis now as a non-expert in about a minute. And people are starting to do this. What I'm showing you here is some panels that were made by a user of simulation, where they've made 800 ply thick, about 6-inch thick, about double the thickness here. And you can see the quality is absolutely excellent, and they were able to get totally acceptable cure cycles. If these seem small to you, another well-known example now is that, remember that DARPA program was in the early 2000s. Just a few years later, the Boeing 787 program launches, and that Boeing team, led by Dr. Nelson, comes up with 2 cure cycles for these huge barrels, and it's called cycle 297 because that was the 297th iteration of the simulation. And this is the prediction. Note there's no axes on this because obviously that would leak proprietary information. This is the actual results of a pre-production run to validate the simulation. And if you actually overlay that, you can see that the simulation did an excellent job. And this was done, as I said, in the very early 2000s. Boeing actually extended that when the 777X program was launched. Boeing went a step further, and they said, can we actually use simulation not just for the part, but for the autoclave? And by coupling computational fluid dynamics with that kind of thermochemical simulation, they were able to design a very sophisticated longitudinal flow autoclave, which was then, of course, patented. Now, the key point I want to make is that thermal simulation, for example, is not just for big companies. It's not even for aerospace. Here's an example of a small high-performance carbon fiber component company who make very high-performance carbon fiber cranks, how they use simulation to help them. So the way they make these cranks is that they consolidate and cure them in a hot press. It's a carbon epoxy prepreg from Toray, and their standard cycle was 12 minutes. They wanted double production. The press was their bottleneck because the crank spending 12 minutes there, that was their most expensive piece of equipment in the factory. They could not afford to basically put in a new press facility. So they came to UBC, and what we said was, can we use process simulation to help them? We made a very simple cure kinetics model of a tiny fraction of the effort that would have gone into, say, that airplane, the 787. And based on that, we were able to identify that the material was gelled and, in fact, vitrified within 6 minutes. So this was an obvious candidate for a cure plus post-cure approach. And all of a sudden, the process time was brought down to 6 minutes. Of course, they did a number of tests to prove that the performance was identical, and they were able to double production at a proportionate cost that was absolutely within their capabilities. If we move past thermal analysis, ask what else is very mature, process-induced deformation, tool compensation, understanding how your geometry changes. That really is quite doable now. Again, there's always exceptions, but on average, what we're looking at here is the 777 abstract trailing edge fairing, and you can take a CAD model, export it, mesh it, then run it, do a thermal simulation to make sure that the thermal history is correct, and then run a PID simulation, and you can see that the PID simulation does a great job of predicting the springing of this structure. This is actually a case study that was done way back, I believe, in the 1990s using 2D models And it's a lovely example of showing how the science improves, but the technology improves so that you can practice faster and faster. Another one, which was done more recently, was to actually use the cycle to reduce the process-induced deformation. Here we're looking at a wingtip trailing edge spar. In this case, it was a BMI resin, so it's a high temperature resin. And what you have is a very complex manufacturing process in terms of the mold. And so you get into lots of technical details. How much of that detail should you remove? But again, these are now things that are increasingly well understood. You then get your prediction. And then what was done, the baseline cycle was modified to get the lowest possible deformation. And in fact, the simulation led to a 35% reduction in the process-induced deformation. Again, all the time as we try to share the capabilities of process simulation in industrial practice, we come up against the issue of proprietary information. So again, you're seeing a scaled, a normalized prediction here. What about in production? Where are we in production? One thing that I believe is really important and gets me very excited as an academic, as a researcher, is the ability to propagate uncertainty in simulation. I think this is really important because as engineers, if you talk to practicing engineers, they don't expect perfection. They are quite comfortable with the idea of managing uncertainty as long as you can quantify it. So what I'm going to show you is how you can propagate thermal cure model uncertainty through a process simulation so that you can actually predict what's going to happen at the end. Let's look at a very simple example. I'm going to take a laminate. I'm going to encapsulate it in silicone so that I get huge thermal lags through the thickness. And I'm going to control the air temperature. And I'm going to ask myself, what's happening to the temperature in the middle of that laminate? The answer is that you can actually, well, in this case, I'm actually showing the true TC data, but you could predict that. And if you actually feed into that your uncertainty with your heat transfer coefficients, your material model, what you would actually get is this blue profile. So you could get a prediction that if you actually quantify the uncertainty would say you can have a huge exotherm, which is totally unacceptable, or you could have a exotherm that is acceptable. So then you ask yourself, where do I go from here? And the answer is, I can now get into data assimilation. What I can do is say, but what if I have other information, not a thermocouple in the laminate, because I'm trying to avoid that. But what if I put a thermocouple on the silicone bladder? You can think of this as a thermocouple on the tool. Can I now improve my prediction based on this new information? And the answer is yes. If you actually now update your prediction because you have more knowledge, you can actually really tightly bound the prediction. And these are the kinds of things that Argonel will show in CAMX in a couple of weeks. And we're going down the path of trying to really, really formalize this. And conceptually, of course, this can be propagated through the whole process chain, thus making all simulations probabilistic. This has been pushed increasingly into production. Remember, every aircraft part must show thermal compliance. So you got to show that it's within a range of temperature increase, temperature hold, and so forth. And the problem is that very often, especially you're making lots of little parts, the airflow interferes with all the parts in there. And so you end up getting very complex airflows depending on what you have in the autoclave that day. To date, this is typically dealt with by having experienced personnel who use their accumulated know-how. Clearly, we want to go past that. For one thing, those experienced people are retiring. Clearly, we have better scientific-based tools. And so a while ago, 9 years of production data was analyzed from one autoclave. This was a collaborative activity between Boeing Winnipeg and Convergent. And 4,000 runs, 75,000 parts, 200,000 thermocouple traces were analyzed. And out came a wide range of HTCs and all sorts of insights. Not surprisingly, thermally massive tools take longer to get to dwell than thermally light tools. And all of this has been used to create new generation of cure inspection reporting tools, where at one end, you're basically doing what you were already doing using an Excel spreadsheet, but you're doing it more methodically. You're getting the same data, you're creating the same reports, though now, if there's a discrepancy, you can use the simulation tools to look into it. But from my perspective as a researcher, even more excitingly, you now have that data which can go into manufacturing analytics. You can look at that, you can analyze it, and you can actually then use that to do what you might call smart loads. Finally, let's do a quick example of how we could push things even beyond this. So what I'm showing you is really well-established stuff that is starting to be introduced. And let me just finish off with some forward-looking example of simulation in production. If you talk to automation people, and I'm very grateful to Dr. Homayun Najaran for this, automation at its simplest level is sense, think, act. You sense something, you analyze it, you act on the basis of that. The problem we have in composites manufacturing, say in automated fiber placement, what should we sense? What do we do with it? How do we run our automated fiber placement better? So in a project funded by the US Air Force by Dr. John Russell, when he was still at the Air Force, we worked with our colleagues in electrical engineering, and we developed these smart rollers. So it's a plug and play roller. It measures at the moment pressure. Shortly, it's going to measure shear, and it will also measure temperature as a bonus. John Madden's group are designing the fingers for the Honda robot. So this is very much their expertise. But these capacitive smart pressure sensors measure the local pressure as the roller moves over a part. And the question becomes, well, what do I do with this? Because if I just measure pressure, that's not enough. Well, what we've started doing is combining this with physics-based TAC models developed under a NASA program a few years ago. And what you can now do is understand how pressure, temperature, velocity give you TAC. And then what you can do is start looking at what happens when you start steering and that pressure and that shear interact. And we know there's patents out there that say, for example, if you want to go around the curve, apply shear, because what gives us wrinkling and other defects is actually the bending. What you're seeing here is a little micro AFP machine running at 0.7 meters per second with high-speed DIC showing the development of the wrinkles in real time. So you can see a world where we're sensing, we're making things, and we're using process simulation to understand what is going on. So let me bring this to a conclusion. Process simulation is the most mature of all the digital manufacturing solutions. And hopefully I've convinced you that it's what allows us to bring together all these things that happen during the manufacturing of a composite part. So it really is the foundation for making use of all the other digital capabilities that are now ever more available. A structured approach using state variables that considers the whole workflow will give us maximum value in practice. Huge amount of science being developed. There's a pipeline to use it. It would be great if that science is developed and shared in a manner that makes it easy to just plug it in, just drop it into the framework. That will make the movement of the TRL levels as fast as possible. In turn, the technology platform needs to be integrated and maintained so that it can actually be used to maximum effect. And finally, I hope I've convinced you that process simulation is not just the code. It's the integrated combination of the science, the technology, and the understanding of the application needs. When you put those together as a whole, that's when you start getting maximum value in practice. With that, I'd like to again end with acknowledging my colleagues, our collaborators, and again, acknowledging that anything you've heard is my biased view and is based on many examples from our own work. With that, I'd like to thank you and answer any questions there may be.
Thank you very much, Anush. This has been a great presentation. We have some questions coming in. Please make sure that you write them in the Q&A. So for the first question, how did the TG profile of the composite look like after optimization? I am thinking it improved by a lot. If so, was there any difference in TG profile amongst different resins?
Okay, so the answer to that is that the glass transition temperature of a thermoset is, putting aside physical aging for a moment, I don't want to make it complicated, is uniquely related to the degree of cure. So if you get the right degree of cure, you're actually getting the same glass transition temperature. So that's in the fundamentals of the definition of TG and degree of cure. So you get the right degree of cure, you're getting the right TG.
The next question, have you started to explore how AI technologies can be applied in the types of simulations that you have illustrated today?
Absolutely. I think if you go back and maybe I didn't do a good job of explaining it, but those very fast simulations that you saw where I said that it took 50 seconds to do something that it took 8 hours, what you're doing is you're using machine learning AI to create what we call surrogate models. And those surrogate models run much faster than the pure physics-based model. You use those to explore the space, but then the lovely thing is you go back and you confirm that the final solution is correct by running the full solution. So to me, the use of AI, the use of ML, they're tools that we use in the framework of physics-based simulation.
Thank you. For the next question, hi, Professor. Great to see you again and wonderful presentation. My question is, what is your opinion on the large computational power that is needed? Sorry, that's good. The next one, are there any process improvement techniques in works for core panels, sandwich panels to eliminate moisture or disbalance?
Oh, I'm sure there are. I know there are. Obviously, I'm here as somebody who's talking about process simulation. So let me answer that with a bit of a process simulation background. One of our weakest areas is, in fact, porosity prediction. There's been some big advances in the last few years. There was some great work done under the NASA ACP program. And the way to deal with this, of course, is to understand how moisture gets in and then how we can push moisture out. So I would say that, yeah, there's advances. It's still low TRL in terms of being able to use it, but the science has improved a fair bit. University of Southern California, Delaware, McGill are places where I would go to look for what they've done.
Thank you. Next question, great overview presentation. In thermosets, the critical area is heat up due to gel, vitrification, and dimensional change. In thermoplastics, the critical area is cool down, particularly for semicrystalline materials. Can you comment on the different approaches and maturity for both?
Thank you. We actually had an opportunity to have a talk on thermoplastic composite simulation with SAMPy. So I encourage you to go and look at that presentation where I spent my whole time talking about thermoplastic simulation. But you've put your finger on what the difference is. From a pure numerical perspective, running the models in cool down versus heat up is trivial. The issue is getting good material models, getting the correct histories, because as you said, the rate of cooling is critical, and therefore getting the model to predict what's really going on is very important. But the good news is that that area is progressing very fast, learning from thermosets, but acknowledging the differences.
Thank you. So the next question, any thoughts on how to incorporate process simulations into system-level modeling to understand the virtual factory?
Yes, this is such a big interest of mine. As I said, process simulation properly done, what you're doing is you're defining a bunch of state variables that at any instant fully define the material state. So take a part that's being laid up. At any instant, if I know how many layers are there, what their thickness is, what their degree of cure is, what their temperature is, a whole bunch of other variables, I know everything about it. I also know where it is. So I start combining discrete event simulation, so basically the logistics of moving through the factory, with this asset state simulation. And when I combine process simulation with that discrete event simulation, I have all the makings of my digital twin. All I need to do is have some pretty graphics.
Thank you. For the next question, the marine industry is also low volume, but relies heavily on worker skill and doesn't have the regulatory requirements of aerospace. What does it stand to gain from process simulation? How do you convince the decision makers to adopt it?
Lovely question. Whenever we look at some other discipline, some other sector, we should learn both the good and the bad. The good of aerospace industry is that they're rigorous in tracking things. The bad is, of course, they have a huge amount of bureaucracy. So if we look at the marine industry, you don't have those requirements, but you want good parts. I'll give you an example. There was a boat builder in British Columbia who made their boats and sold them around the world. And what they discovered was that the boats that they sold to Australia, that they made in the winter in northern British Columbia, had lots of warranty defects. In working with them, we discovered that they brought in the tool from outside, and in the winter, that tool was cold. It was a room temperature cure. Even though they did exactly the same thing that they did in the summer, the degree of cure was lower. The degree of cure was lower. Water would come in, and they would get blistering. Therefore, I would say to you that the way to prove that you should use process simulation is by showing that there's value to you in a cost-effective way. And that's why I gave the example of the bike company. You don't want to use process simulation the way aerospace does. You want to use it much simpler and right-sized for your industry. Be very happy to talk to you about that in a conceptual manner.
Thank you. The next question, do you see knowledge engineering / semantic web technology as a route to pulling together all of these threads, creating open ontologies, data schemes, and taxonomies, for example?
Absolutely. And you notice that I'm the co-director of the Composites Knowledge Network. I'll put in a shameless plug for the Knowledge and Practice Center, which is a step towards that. It's the beginning of a journey. We believe that to do that, we have to bring together the whole community in a sort of non-competitive fashion. Thank you, Casey. He just put the link there. Casey is the director of the KPC. But yes, we need that kind of stuff because that provides the background to use all this new capability.
Thank you. And we have time for one last question. How effective is this to identify wet and dry locations in a composite laminate?
Sorry, can you repeat that?
How effective is this to identify wet and dry locations in a composite laminate?
So I assume we're talking about infusion. And there's some very good infusion software out there. It's not something that I do, but there's commercial software, Moldflow, PAM-RTM, academic software such as LIMS from the University of Delaware. And again, if you set them up right, they should do a very good job of predicting.
Thank you. We have time for one last question, this time for reals. Great presentation. With the development of next generation matrix materials such as Vitrimers, what do you expect will be the bottleneck to their implementation by the composites industry? Generating material property data, or perhaps the modeling of new polymer physics such as dynamic bond exchange?
Lovely question, and a topic that I'm desperately trying to understand, because that's exactly the issue. The chemists are always ahead of us. And that's again why I believe in a very structured approach to these things. How do we do vitrimers? So it'll be the usual thing. We need to understand the science. Based on the science, update our definition of what is transformation. But if we do it right, then we just plug that into the next hierarchy in the model, which is the thermal model. And if you do it in a state variable way, introduction of that new material will be much faster because we can harness simulation to help us. Don't know who asked that question, but again, love to talk about that because I think that's a really cool question.
Thank you, Anush. I can put you in contact with both of them who you mentioned if they're okay with that. We can have that exchange offline. And with that, thank you so much. I'd like to thank you for such a great presentation, for your time, and for everyone to attending this webinar. So thank you. And if you have any more questions for Anush, please feel free to reach out either to him if he's okay with that.
Absolutely.
Or to myself, and I'll redirect the questions directly to Anush. So then again, thank you everyone, and stay tuned for more of the webinars that are hosted, as I said, every month by Sampi. So thank you and have a good morning and afternoon.